All right, so this is homework 7. And it's introducing something called complex numbers. And the idea here is a little crazy, I guess, right? It's called an imaginary unit. That's the key to these complex numbers. And the idea is that if you see the square root of -1, in the past we've said this is not a real number. So that's true because the square root of -1, if it were to equal something, let's call it I, like an X or Y or whatever, an A, right? So if we say this equals something, then we know from our definition of square roots, then I squared has to equal -1, right? But of course that means none of the numbers that we're used to working with, none of the real numbers have this property, right? Every number that's real, when you square it, you get positive number. So this I is something else, but it can still be thought of as a number. It's an idea. You know, in the same way, like 5 is not actually a thing, right? It's not like a chair or a desk. A number represents an idea, right? We know what 5 means, right? When I hold up 5 fingers, we know that's really can represent the number 5. So we have a symbol for it and it has a meaning. And it's the same thing with I. Okay, so even though maybe we haven't worked with it before, it's still a number in the same way that 5 is a number. In the same way, actually, I'm saying this because some people don't like the idea of this I, like it shouldn't really be there or it doesn't exist or something. But if I write down the square root of 2, pretty much everybody accepts that that's a number, right? But really, this number, if I were to write it out as a decimal, it's a decimal that I can't even remember exactly what it is, but that decimal keeps going forever and ever and ever, and it never stops and never repeats. So this is also not a number that you can sort of like hold in your hand, right, in the same way, but it has a meaning. The square root of 2 is this number, whatever it is, and when I square that number, I get exactly 2. That's what the square root of 2 is, even though I can't actually like sort of work with that decimal number. I have no problem accepting that that number exists and I know exactly what it does. And I is the same thing. So I is defined as the square root of -1, or I squared equals -1. And we want to, in both of these cases, we really want to move sort of this direction. So if we have the square root of -1, we actually prefer to write that as I. It's called the imaginary unit. And if we have an I squared, I prefer to write that and change that into -1. So this direction is sort of simplifying. And so what that does for us is now we have a way of actually writing some things that we couldn't have written before. So if I give you the square root of -4, well, we know from square roots, I can think of that as the square root of -1 times the square root of 4. The square root of -1, well, I now know what that is. That's I. And the square root of 4 is 2. And we normally like to write it in that order just because it's kind of like an X, right? We like to put the coefficient first. So now we have an expression or a way of writing some symbols, which is this new idea, right? And so no longer are you allowed to say the square root of a negative number is not a real number, or sometimes people say it doesn't exist, which is not quite correct anyway. But now we know exactly what it is. The square root of -4 is 2i. And we can see that that's true because if I square 2i, I get 2 squared times I squared, which is of course 4, and I squared is the same as minus 1. So it is a number that works, right? It sort of does what I want it to do. And so what we can see here is because this minus 1 just comes out as a factor, really anytime I have any square root of a negative number, no matter what that number is, the I will come out, right? It pulls out the negative 1. You know, if you think really deeply about this I, it could kind of keep you up at night, right? Like, what? How does that? What? But and I think that's good to a certain extent to think deeply about it. But it's also fine here to just say, well, okay, I know what it's supposed to do, and I'm going to do that, and hopefully it'll begin to feel more comfortable as I work through these problems, right? So one set of problems, and this is probably what we use mostly going forward, is just dealing with this. It's the same old simplifying square roots that we did before, but now there can be a negative inside the square root. It doesn't really change anything. It just pulls out as an I. So if I give you the square root of negative 24, well, we're going to factor that negative 24 as a perfect square for and the 6, which is the non-perfect square. This becomes 2i square root to 6. Okay, so so that's one part of working with this imaginary unit, and to be honest, probably the most important part. We will see this as we move forward into our next section. Any questions on that part?
Can you do one where the square root is cubed?
Yeah, so I can do a cube root, but here's the thing. If I give you like the cube root of negative 8, we no longer have the square root of a negative number. So a cube root, it turns out, is not going to generate this imaginary unit, this I. Turns out with a cube root, the negative can come in and out easily of the cube root because when I cube a number, right, it's negative 2 times negative 2 times negative 2, and because there's 3 negatives, that gives me a negative 8. So when you're working with cube roots, even if I have like the cube root of minus 5, this is equal to negative the cube root of 5. So like the negative is sort of I don't want to say a non-issue because you got to pay attention to it. It's still there, but it doesn't create this imaginary unit when we have cube roots. Now, fourth roots, we can get into a little bit of some complicated territory, but we won't see any of that in our class. Right? Like, what's this? You know, this sort of opens the idea, like, well, what's the square root of I? Square root of a square root of negative 1, and you can talk about it and define that, but we don't need to for our purposes. Okay, so does that now? I mean, this doesn't change the negative here. Doesn't change that we still have to do some work sometimes with cube roots, right? If I give you the cube root of negative 250. We got to try and figure out what perfect cube factors are there. And remember our perfect cube factors here, we're looking for factors of 8, right? That's 2 cubed, 27, 3 cubed, 4 cubed is 64, and 5 cubed is 125, right? So that's minus 5 cube roots of 2. Cube root of minus 125 is minus 5. Um, other questions about this? It's at the end of our chapter, but you can really do this. We could have put it more in the middle of the chapter too. It doesn't rely on much of the other things.
What
Okay.
about graphing?
Well, that's a good, like with imaginary values.
Yeah.
Well, that's a very interesting question. So, okay, before I can get to that, I need to define what's called a complex number. So the imaginary unit is like a single number or kind of definition, and it allows us to talk about these other kinds of numbers that involve I. And so we need to kind of define like a complete structure of those, and the structure that includes all those imaginary numbers are called the complex numbers. So a complex number looks like A plus BI, where A and B are real numbers. So remember, your real numbers are like 17 and -2 and square root of 7. Like all of those numbers are real numbers. So a complex number is something different. It's where we have a real part, we have an imaginary part, and the number may include both parts. It may include only the real part, which are like the real numbers, and it may include only the imaginary part, which are like the purely imaginary numbers. So this is like combining that imaginary unit with everything else, and it creates this set of numbers called the complex numbers. And if you go back to, I don't know if we talked about it in the beginning, well, maybe briefly, you know, we have these different sets of numbers. We have like the whole numbers, and we have the integers. Integers. We have the rational numbers, which we've talked about, right? Those are the fractions. And we have irrational numbers. Those are like the square roots. And if you put those together, you get the real numbers. And then if you add in like the imaginary values, you get the complex numbers. So like these are all different sets and sort of contained units of numbers. And it turns out like with integers are positive and negative whole numbers. And if you add or subtract these, you always just get another integer. So they're called closed under addition and subtraction. And what that means is that you don't need any other numbers. If you start with integers and you add and subtract them, you stay in integers. But as soon as you start introducing the idea of division, integers don't get it done, right? You can't divide 3 by 2 and get an integer. You get something else. And that other thing is called a rational number. So rational numbers are good for addition and subtraction and multiplication and division. You can do all those operations and it's fine. You stay with rational numbers. So you sort of feel like, okay, rational numbers are enough. But then all of a sudden, if you introduce the idea of kind of square roots, rational numbers aren't enough there. And so you then get this set called the irrational numbers, and you put all those together and you get the real numbers. The real numbers are great. They've served us well all the way along, but all of a sudden we're getting into a spot where we need more, right? And it turns out we need these idea of complex numbers, and the complex numbers are closed under all of this basic algebra. So adding, subtracting, square roots, all of those things, if you start with complex numbers, you stay in complex numbers. So they're a big enough set for us to work with for, well, the a while, a long time, potentially. Like, I don't know, if you're a math major, you'll bump into some other numbers, but for a while, the complex numbers are good enough for us. So that's like a little sidelight of kind of the structure of what we're working with here. So these complex numbers look, like this, a plus bi, so 2 minus 5i, or 17 thirds plus the square root of 2i, 53i, 5 halves. These are all complex numbers, okay? This one is got real and imaginary, real and imaginary. This has only imaginary part. This is only a real part. So all of these are complex numbers. So they cover everything. It's like your biggest possible set. And so you can do some basic operations with these complex numbers, and that's part of what you're doing in this section, is adding and subtracting or multiplying them together. And you'll see you still end up with a complex number when you do all those things. But the question originated with graphing, like can we graph these numbers? When we typically look at our XY coordinates, this like point here includes both an X and a Y, but X and Y are both real numbers. Okay, so if I'm looking on this coordinate graph, there is no 2 minus 5i. That's a number, and it is not present on here because X and Y are the real numbers, right? When you look at, even break it down kind of more simply and just look at the number line X, the number line equals real numbers. There's no spot there for imaginary numbers. So for our purposes, an imaginary number doesn't show up when we're looking at our typical graphs. Okay, so that's the short answer. However, you can, this is like the extra kind of bonus answer, you can plot. So like if you imagine the real numbers, all you need is a line. A line includes every real number, right? I start at 0 and I can put every real number somewhere on the line. They're organized, they're ordered, right? Larger numbers over here, smaller numbers over here. The complex numbers are not ordered in the same way, and I can't graph them on a single real line like that, but I can graph them on the complex plane. So I can sort of co-opt this Cartesian plane and write my number a plus bi with a real part and an imaginary part. So I put the imaginary part on the vertical axis and the real part on the horizontal axis, and I can represent this one number with a point. So I don't want to spend too much time on that in class because we're not going to see that. But it's an interesting idea, and it's really different than this plot, right? This plot is representing two numbers, both real. This plot is representing one imaginary or complex number. And this is another way of representing one real number, right? So if you wanted to plot the real numbers here, they would just show up on this line, right? But then there's all these other possible numbers, right? It's like, theoretically, this is like a mind expanding experience, right? To be like, okay, I thought my numbers were like this, but whoa, there's actually a whole bunch of numbers that I wasn't seeing out there, right? Lots more numbers. Okay. And again, a number is amazing, but it's also just a number, right? All these things just represent single ideas. For those of you that are feeling a little maybe swimming in the deep end here, don't worry. the tasks you're going to be asked to do are much more straightforward and specific, not these conceptual tasks. So with complex numbers, we want to be able to do things like add them together. And it turns out that you can add or subtract them kind of the way you would expect, like the real parts go together. 2 plus 5 is 7. And the imaginary parts go together. 3i minus I is 2i. So that probably is sort of naturally how you might want to add them together. 3 minus 4i times 2 plus 5i. So you can also multiply them together. And here you should FOIL, right? Because it looks kind of like you really treat it just like these are x's in terms of the foiling of the patterns. 3 times 2 is 6, plus 15i minus 8i minus 20i squared. The difference here is I squared is not like x squared where I just have to keep it. I know what I squared is, right? If I go back to the beginning, I squared is minus 1. So anytime I see an I squared, I want to replace that with a minus 1. Minus 20 times minus 1 is a plus 20. So I get 26 plus 7i. And notice that is now written in that complex number form. So it appears just from these two examples that if I add two complex numbers, I get another complex number, which is actually always true. And if I multiply two complex numbers, I also get a complex number. So this is closed, to use that term, under addition and multiplication. Turns out subtraction and division also. Okay, so kind of a long answer there, but did that help, or were there other other questions or specific problems that we should look at? Okay. Okay. Any other like general questions about imaginary numbers? I hate the name imaginary number. I know hate's kind of a strong word, but because it implies it's like a bad joke, right? Because it's a number that's not real, so it's imaginary. Haha, you know, it's not funny, but it makes it seem like it's made up, you know, imaginary, but it's not. It's a thing. It's an actual value, right? In the same way that 2 is a value. It has different properties than 2, obviously, but it's still a number. So don't let that terminology, imaginary number, throw you off. It's like just the name for it. Okay. Any other questions about any particular topics or okay. I wanted to go over just a couple examples from homework 6, which are equations. with radicals? Hopefully you're feeling more comfortable with simplifying radicals. Right, that's a really important skill, and you'll see some of those for sure on the quiz, but also on our final exam, working both with square roots and cube roots and being able to simplify or reduce those expressions. Maybe luckily, you don't actually have to do a lot with simplifying radicals when you're doing equations. And we should know this from our last section too. Equations introduce some new abilities for us because we now have two sides and we can try and keep it balanced, right, in a way that we couldn't when it's just an expression, right? So if there's no equation there, then of course we don't have the two sides anymore. But when it's an equation and you've got radicals, your goal is to eliminate the radical, possibly radicals. In the same way, when you have an equation that has fractions, your goal is to eliminate the fractions. And then you deal with what's left, right? Sometimes when you eliminate that, you get different types of equations. But you want to start by getting rid of the thing you don't want, right? So when you have a radical, you don't really want that radical in there. So for example, the square root of 3x minus 1 plus 2 equals 7. Okay, so here's an equation. You can see that because the equal sign, but you gotta recognize it and look for that. There's our equation. I'm not trying to actually solve it to get the answer right away, right? What I'm trying to do here is make it better, and making it better means getting rid of the radical. And our strategy for that is we are going to square both sides. Okay, so that's an operation you can do to an equation. It turns out it's not perfect. What I mean by that is like a perfect thing is adding something to both sides. When we add something to both sides, we don't change the equation, the solutions at all. It's exactly the same solutions as what I started with. When we square both sides, we have a little bit of a chance of changing the solutions. Luckily, we don't lose any solutions, but you might add some fake solutions. They're called extraneous. Okay, so square both sides, we have to understand that might add extraneous solutions. Okay, that's a possibility. Now, the problem or the thing to watch out for is that if you square both sides, I don't get to square each piece. That's not algebraically the same thing. That's going to change the equation. What I have to do is square the whole side. If I square this left side though, because it's a sum, I'm actually going to have to FOIL that out. It's like when you square x plus 2. You can't just square the x and square the 2. You got to FOIL that together, and it creates a much bigger expression. So in this case, we don't actually want to square this because it's going to be a mess right now. What I need to do first is subtract the 2. So I call that, you got to isolate the radical. So what that means is I need this radical, the square root, to be alone in order for the squaring to work and get rid of that expression. So make sure you do that first. Now I'm in a good spot here to square both sides. Square root 5 is 25, that's fine, that's whatever. But what happens here is what's critical, right? This is a square root, and when I square the square root, those are exactly opposite operations. So all I end up with is 3x minus 1. These like, I can't really, they cancel each other out, right, when you square the square root. And then I end up with a nice, easy equation. In this case, it's just linear. 3x equals 26 and x equals 26 thirds. I do have to check it, right? Remember this, I might have, when I squared both sides here, I might have added a solution that was like a fake solution that doesn't actually work. So it's possible this doesn't work. But when I plug it into the equation, I can see 26 thirds times 3 gives me 26. 26 minus 1 is 25. Square root of 25 is 5 plus 2 is 7. So this does work. But a lot of times you'll get ones that are like close. They're just off by like positive or negative. And if you don't check, you'll type them in or write them down and you'll be wrong. Not because you did any of the steps wrong, but just because you forgot to check your answer. This is a little different than other problems, right? In other problems, if you did all the steps right, you got the answer right. You didn't have to check it. But here we really do need to check that. You know, the example that I always give is to say, let's say this, let's just keep it simple. X equals 2. Right, let's say that's the equation we start with. Very clearly, the only answer there is 2, right? I don't need to solve it or do anything. But if I square both sides, I get that x squared equals 4. And notice here, we actually have two solutions, right? For x squared equals 4, that says x equals 2 or x equals minus 2. So by squaring both sides, I have introduced a new solution. But when I try the solution back in the original problem, certainly minus 2 does not equal 2. So that's an example of an extraneous solution, right? When I squared both sides, I added an extra solution that didn't really work in the original problem. I didn't lose the solution that I started with, but you can add more. Questions so far? Okay. This one was a pretty simple or relatively straightforward version. It had this tiny complication of having to isolate the square root. Let me show you one that's a little more complicated. Square root of 4 minus 3x minus 8 equals x. Sorry. Well, it's got a square root and it's an equation. So just like before, I want to isolate the square root and square both sides. Right, so I move the 8 over, that's fine. And now I square both sides. Just like before, the square root and the square give me just what's inside, 4 minus 3x. The right side is where, I don't know why, but I see tons of errors here. Everyone just wants to write x squared plus 64. But that's not correct because I'm squaring a sum. I actually talked about this when we did the other problem. that's really x plus 8 times x plus 8. And when I square that, I have to FOIL that out. I get x squared plus 8x plus another 8x. So I actually end up with x squared plus 16x plus 64. Really important. Otherwise you get the problem wrong. You do a lot of work and you end up with not a good result. So this is better here because there's no square root anymore, but it is, notice, a quadratic. That's fine, but it's going to take me a little bit of work to do the quadratic. I've got to set it equal to 0. So when I add that over, I'm going to get 19. When I subtract that, I'll get 60. And now I want to try and factor that. Right, it's x and x. It may take a little bit of time, but you'll get there, I think. 2 times 30, 3 times 20, 4 times 15. 60 is kind of a bad number, right? 5 times 12, 6 times 10. I didn't have to go through all those, right? Because there's the pair that gives me, adds up to 19, right? So this is x plus 4 and x plus 15. Now, just like before, I got to check these. I don't know if those are, excuse me, if those are both solutions. It's possible. Maybe just one of them's a solution. That's possible. Or maybe none of them are solutions. That's also possible. So everything is still on the table here. I don't know what's going to work. When I put in minus 4, I'm going to get the square root of 4 minus 3 times minus 4 is plus 12. Minus 8 should equal minus 4. That's 16, and square root of 16 is 4. So that's good. That one checks out. And I do the same with minus 15. Four minus 3 times minus 15. Minus 8 should equal minus 15. Just plugging it into our original formula there. That's 4 plus 45. That's 49. That gives me 7 minus 8 equals minus 15. It's close, right? Sort of dangerously close. If this were only minus 7 instead of plus 7, it would have worked. But it's not. It's plus 7. So this doesn't work, which means this was actually an extraneous solution. And unfortunately, they're always that close because you get the extra solution by squaring both sides and kind of eliminating the negative. And so you're always just off by a negative with these sort of fake solutions. So it turns out the only answer here was minus 4. Questions about that one? I mean, I'd argue that's a pretty significant problem. Zoom out here a little bit so we can see the whole thing, right? it's not trivial by any means. You gotta isolate the radical, square both sides, do this algebra properly. You gotta recognize that it's a quadratic, so you move it into the standard form. You gotta remember how to do your factoring and solve those. And then finally, you have to go back and do some basic work with the radicals for checking your answers. So this is, I think, in some ways like the pinnacle of the work we've done this semester, right? A lot of the things that we've been doing have kind of led us to this point. The square root portion actually is not that significant of the problem, right? I mean, we're really kind of done with the square root, like right here, right? All the rest of it is kind of old stuff. And then we just come back to do a little bit of square roots at the end. But so this is one where, you know, you're very capable of doing all of these steps individually. It can be challenging, right? You got to keep track of what you're trying to do as you work through that. That comes up when you have like an x on the other side. So then when you square both sides, you get an x squared. That's going to be a quadratic. That's going to take a little extra to get to your solution. Any questions? Anything about any of the other problems? Anything else about the course? I think I mentioned it last time, but it's the right time to go and think about registering for your next course. If you haven't already, I really encourage you to, you know, keep moving ahead with math. For most of you, that means 1150. But you still have some choices there about, do I take it in the summer? Do I take it in the fall? What time or structure works out? Some classes, there's not much in the summer, I think, that's face-to-face, but there are some in the fall that are face-to-face. So depending on how comfortable you are with both online learning, but also, you know, being vaccinated or wherever you are in that process, there's a lot of variables here at play, and it's good to pick the course that works best for you. So if you wait around, you might not be able to get into that course. It's easier to register early, and then if you have to change your mind, you can change your mind later. But it helps if you can get registered now. Sometimes courses get canceled if you don't get enough students in them. So you might be thinking, oh, this one's fine, it's got lots of space, but it could go away if you don't get in there. So if you have any specific questions, please, I'm happy to help, or your advisor can also help. They would know what to do too, but I would be perhaps better with the math recommendations. They would be better with sort of how everything fits together with your schedule and some of that information. So those are two important resources to take advantage of. Okay. Anything else? At least I got a couple questions there in the beginning, so thank you for that. And like I said in the schedule, we are closing in here on the end of the course, right? You have your homework from this section due on the 20th. Our next section is due on the 4th. And then we have our exam, our midterm exam, the Monday following that. So our midterm is in 3 weeks, right? So stay on top of this material. It's probably a good time to start thinking about your final exam kind of review or cheat sheet. You can start putting that together with this information and from the next section. And, you know, keep up the good work. Okay, so I hope to see you all next Monday as well, and stay warm, and Yep. Take care.
Thank you.
Thank you.
Take care.
Yeah.
Thank you.
You're welcome.